Okay, welcome to this continuation lecture series for Polystyrene Lab in Material Science 410. Last time we talked about generic chain growth polymerization and some of the implications at the commodity plastics level and recycling. So here we'll look at some of the details of the kinetics and think a little bit about some of the mechanisms for initiation, propagation, and importantly, termination reactions that will limit molecular weight and ultimately the progress of the reaction. So as we mentioned before, chain growth polymerization tends to be dominated by radical polymerization, so the middle row of information that will appear on your screen. But we recognize that anionic and cationic mechanisms exist as well, and there are parallels between every step that we'll discuss for radical polymerization. When we focus on initiation, we see that an initiator is going to be needed in the form of a radical, and this fragment of this initiator molecule is responsible for transferring the reactivity of the radical to the monomer listed here. All right, so initiators, examples of that will be listed in just a moment. So we'll learn the identity of Y dot in just a moment. But we'll see that the Y dot molecule is responsible for adding to the monomer to generate our first covalent bond and to propagate the radical position to the end of that monomer. The steps for that are analogous to the first propagation step that we see here, where we're going to use half reaction head half arrows to represent the mechanism for that covalent bond forming. So I'll just show that over here with a Y, and we'll put our dot on this side. What we want to do is show how we make this first covalent bond with our radical fragment Y dot. So we're thinking about making a bond right here, so I'll abbreviate that with a dotted line to show where we're going to make that bond. Bond, of course, has to have 2 electrons, so we're going to show 1 electron coming in from that radical, and we're going to borrow that second electron from the double bond. This is why most monomers for chain growth polymerization are unsaturated. They have either a double bond or a triple bond available. So here we go. We've now used 2 electrons. We now understand how the 2 electrons in this Y to carbon covalent bond have been formed. That double bond was compromised, so there was one of the 2 in the double bond used, and we've left one bond untouched, of course. And so to show where that final feature goes, we're going to position that on the other end of the molecule to satisfy valency and bonding requirements at every carbon. So if you follow me on this, the end result is we've formed this covalent bond from the first 2 half arrows coming together to give us a 2 electron bond. We have lost the double bond in the middle of the monomer and retained only the single bond, and we've pushed a radical out to the end of the molecule, and we see that showing up at the terminus here. That is our initiation step. On screen already is what we need to understand our first propagation step. So it's going to be very similar to what we've already cartooned there for us. So we're going to see, again, half-headed reaction mechanism arrows. We're going to see that radical give us what's needed for our first covalent bond between monomers now. And so we're going to use that radical to give us one of the 2 electrons in this dotted area to become our next covalent bond. Borrow 1 electron from the double bond to give us a second electron for that 2 electron bond, and push that final electron from the double bond out to the final feature. So this might be a moment where you pause the video and try to list what the product here is, given your understanding of how the mechanism of radical reactions work to give us our first propagation product. Okay, so hopefully you were able to predict that we're going to see a very similar feature, now simply covalently tethered to that first one, and that feature is, of course, here. So our blue monomer is shaded differently to help us recognize that. If things are done correctly, we always have to show that new radical in the propagation step. And this again is ready for yet another propagation reaction with another fresh monomer, like the blue one over top, that reaction arrow listed over here. So this will continue, and polymer growth is terminated by a termination reaction. Okay, so we'll talk in detail about what this looks like in the termination reactions part of our video. Okay, so we recognize already that a termination reaction is going to have a radical characteristic to it to help us terminate this polymerization, and we're going to see a couple of options for what the bonding looks like at the end here. In some cases, single bonds are present. In other cases, a double bond will be formed by way of a termination reaction. As we mentioned, a lot of the steps are analogous for cationic polymerization and anionic polymerization, and we won't go over those in details, but for other courses or other components of your future career, you might need to navigate back to content to understand this, and drawing on it, your understanding of radical polymerization can be useful. Okay. So in considering some of the kinetic implications, just at a high level, we'll recognize a couple of things. So radical chain polymerization consists of a sequence of those three steps we just discussed: initiation, propagation, and termination. So we need to separate our view of the kinetics and consider each one in turn. The initiation step is considered to involve two reactions. The first is the production of free radicals, that Y dot that we just saw on the previous slide. Okay, so here, some initiator, abbreviated IN2, needs to break apart to give radicals like we saw on the previous slide. So here, IN2 dissociates into two radicals. This on the previous slide was called Y dot. Okay, so the dissociation of the initiator species yields a pair of radicals typically, and the rate constant for this reaction is shown as lowercase sub d, kd, for the dissociation kinetics and equations there. To give you an example of what is IN2 from the former slide and what are some options for R dot or Y dot from a couple of slides ago, here are a couple of well-known radical initiators. Benzoyl peroxide is a very famous radical initiator. It's based on the peroxide functionality. So if you recall, hydrogen peroxide is simply this molecule. And so we're going to see the same OO single bond in the middle of this molecule. This time not flanked by hydrogens, but benzoyl groups with carbonyl and phenyl groups instead. Okay, so here we recognize that peroxide in the middle. We can see that oxygen-oxygen single bond is very reactive and prone to degradation under heating. So by heating this, we get what's called homolytic. So the same, homo to both sides, lytic, the break. So we're going to break that single bond of the oxygen-oxygen single bond evenly to split the molecule into two fragments. The first product here is listed here, and here we have two radicals where we have an oxygen-centered radical. This radical is so reactive that it further decomposes to decarboxylate. It's going to eliminate CO2 and generate our phenyl radicals, which are known to be the active radicals for initiation. So we've seen these in our earlier slides as R dot or Y dot. Okay, so what happens here is one electron from that initial radical helps form a double bond here. We're going to break our single bond now to eliminate the CO2. That is going to give us the C double bond O to both sides. And then the third electron ends up as our blue feature here in our radical. So again, this phenyl-based radical is our initiator that results from the use of benzoyl peroxide in polymerization. we would see this phenyl group at the leading head of the polymer. Another famous one is AIBN. This can be triggered for degradation using heat or light. So photopolymerization, photopatterning can be enabled here. And here, the reaction is driven in part by the elimination of gas, as well as the reactivity of this azo functionality in the middle here. So here you can see that the driving force is to generate a nitrogen-nitrogen triple bond, so we need to direct in a symmetric fashion one electron from flanking single bonds into the double bond area to give us our triple bond. And so we're going to see that on both sides of the molecule evenly. The remainder of the single bonds here and here end up as our blue dots for our radicals. So this butyrylnitrile is the active kind of group for radical polymerization, and we would also see this tethered to the beginning of our chain growth polymerization products. Okay, so now that we have a better understanding of how we get our radicals, we can move on to understand some of the next steps. So thereafter, sticking with the format of R dot, so this could have been the phenyl functionality, for example. We know that the first propagation step demands a reaction with monomers, so we abbreviate that as M, and that first initiation of the monomer is now going to have a rate constant K sub I, and the product here will be labeled for our understanding here as M1. So M1 is the first monomer on a polymer, so that's where we get 1, and we've got the radical indicated with that dot there. This has its role for now being responsible for initiating other chains, and so we're going to see M1 playing a future role in the next propagation step. Okay. So, since M1 will be required to react with yet another monomer, we can expect a pattern in the equation to look similar there. So M1 will react with a monomer. We'll see another propagation constant here, Kp. So this is technically different than the Ki because we have now a monomer-based radical reacting with free monomer, which was different than the phenyl radical reacting with monomer in the Ki example. So we still distinguish those rate constants purposefully there. After successful reaction, the monomer is now extended. So to molecularly show an example here, we would have the phenyl bonded to the alkene. So I'll put a generic R group there for our first M, and then we would have our second unit here. Okay, so to show you where M is, this is our first M, and our next one is over here, M. So M1, M2, and this was our R dot as an example there. This M2 radical that we've pointed out explicitly here, of course, will undergo yet another propagation reaction by adding another monomer to give us an M3 product. So that would look like this. Okay, again, unidirectional growth, and we're going to see the same rate constant fits there nicely. And likewise, if that trimer with the radical can add yet another monomer, we'll extend the chain to M4, same rate constant. So what we learn here is that since Kp is very large and not really distinguished because the characteristics of the radical at position M1, at position M2, at position M3 are about the same. The chemistry, the environment is about the same. Kp is generically very close to one another regardless of the reaction option that we're listed here. Kind of an interesting feature there of polymerization. So this helps our kinetic understanding a little bit in that we can really only consider one rate constant for propagation. So we script this as a general form down below, where we have Mn, something with a radical, adding fresh monomer, M neutral, reacting with rate constant Kp to extend that chain by 1 unit, so n plus 1. And that's our general equation listing the rate constant Kp. Okay, so to put all that together and to finally understand a rate law for this propagation, we have this. So the rate of polymerization is the sum of all those steps. Kp was the fastest. Rate was very fast, I should say. Sometimes Ki is faster, but it is very fast. And so the rate constants for all propagation steps can be kind of condensed into something far simpler. And so here we're going to see the rate of change of monomer neutral as a function of time. So dm by dt, change in monomer concentration as a function of time. Of course, that's decreasing with time. We're losing monomer with time, so I see the negative sign there. It is going to go with that rate constant multiplied by the concentration of the radicals and the concentration of neutral monomer. So clearly, if we want to have a faster polymerization, we would want to have more initiator to generate more radicals. This would emphasize that middle term, give us a higher concentration of radicals and ultimately a faster rate. Or we could go to very high concentration monomer, perhaps even eliminating solvent altogether to give us faster polymerization, and ultimately we can see the implications there. Again, Kp is mostly set by the monomer selection, and we're not going to see very much impact by going to different. We can't really do much there. Okay, reaction termination. So termination has to annihilate radical centers. We have to eliminate those radicals, and we're going to need bimolecular reactions for that. So in short, we're going to need two radicals to react with one another by one of two options. The first is going to be coupling. So the main idea here is that in coupling, we're going to see R dot react with R dot, and these could be different length polymers. We're going to form an R covalent R type molecule. So if these were different, I'll just put a prime there to distinguish the first from the second. Coupling. Two radicals come together, eliminate both radicals, and we're going to see a covalent bond in the middle. So when we show that with some kind of features representative of the polymer, here's a repeating vinylic polymer with generic R prime as a side chain with n repeat units and an additional one showing the reactive radical. We have a mirror image of that over here. N doesn't have to be the same, it could be different. And we're going to see these two radicals combine and form a covalent bond. Will form in the middle. From this coupling reaction. So to show that with half arrows, we want to form a 2 electron bond. So we'll use both of those radicals, push them together, and show that new bond forming right there. Two radicals have gone into this reaction. There are no radicals in the product. We've annihilated those radicals. That is a termination reaction. Okay, let's clean that up so we can see the next example. So in this next example, disproportionation is going to occur. So there will be a disproportionate set of products. They will not be the same. There will be two products and they'll be different. Okay, so that's one way to remember that. Proportionation almost sounds like protons, so we're going to see a hydrogen transfer. Hydrogen by itself is, of course, just a proton. So here, a hydrogen radical that is beta to one of the radical centers. So this is not directly connected to the radical, but one spot over, the beta position, is going to be transferred to another radical center. So let's see what that looks like. Using those same molecules above, we'll position them here in a similar fashion, a little offset, but again, kind of pointing the reactive groups towards one another. Here what we're going to see is that this beta proton, so it's not directly tethered to the radical site, but offset by one spot, a beta position proton, is going to end up bonded onto one polymer. So this is a hydrogen abstraction. To show how this forms, we'll use those reaction arrowheads again. We're thinking about forming a bond to that hydrogen for abstraction. So we're trying to form this bond here, half arrow there from the radical, and we're going to borrow one electron from the CH bond to give us the other electron for bonding. That leaves one extra electron from that former single bond. That is going to drop down to the carbon-carbon site, and we're going to finally annihilate our other radical by bringing it in to give us our double bond. So if you follow that, you should now understand how we got this double bond by the loss of that hydrogen formerly here. One electron went to help us with the bond over there, and the other electron gave us half of our new double bond feature in this product. These are disproportionate polymer products. One has a saturated carbon terminus, the other has an unsaturated carbon terminus, and we've shown hydrogen abstraction for termination. Okay, so those are the main termination reactions. And of course, we can bring them into our kinetics as well. And so combination, generic molecule M sub n with a radical. Here to show that we could have a different chain length, M sub m will happen. These two radicals combine, we will double the length of the molecule if n and n are the same. If they're different, we certainly do get a larger molecular weight product than we started in for either example. So here we show that as N plus M as the product, no radicals listed there, and we show termination by coupling as a TC sub on our rate constant. Disproportionation, likewise, TD for that rate constant, and here we're going to expect two products at right, radical with N repeat units, radical with M repeat units, no radicals in our products, and molecular weights are about the same. One of them has gained a hydrogen, which is very low in molecular weight compared to the general molecular weight of a polymer Mn or MM. So it's rare that we can consider how both of these terminate two radicals by annihilation. We can put them together to a generic KT, which sort of would encompass both of these terms together to give us our dead polymer. No more reactivity on that. Okay, so I think we've said most of these points. So a combined rate constant approach can also be listed. And to give us our final rate constant equation, we have this here. So KT, that combined, is going to account for coupling and the disproportionation. So that should be a D there. Apologies. And we have some coefficients out front, A and A1, to help us know the relative balance between coupling versus disproportionation and the termination mechanisms at play. So these are fractions of termination by coupling and disproportionation that are occurring there. For example, if A was dominant, we might have 0.9 for A and 0.1 for the makeup for the disproportionation product option there. So to summarize these kind of general approaches to understanding some of the kinetics, we saw that monomer concentration and radical concentration help us propagate and react, and the rate of consumption of monomer is proportional to those features, and that Kp is largely set by the monomer selection, and that these termination reactions will occur should two radicals find each other. Some advantages of general radical polymerization are that they're cheap, they're pretty easy to carry out, they're actually tolerant of many functional groups, so we can even polymerize in water or without solvent at all, so and accommodate a broad variety of monomers that have these unsaturated double bonds for reactivity against the radicals. And we can use several different polymerization techniques, such as heat or light, solvent-free, things like this are easily accommodated. There are some disadvantages. Generally, radical concentration needs to be maintained to be low. So this is disfavoring high rates of propagation because we want to restrict termination reaction, proportionation, and chain transfer. The higher the concentration of radicals, the more likely these radicals will find each other and undergo termination reactions, for example. Generally, these reactions proceed well when you have fairly pure reagents. So if there are impurities that react with radicals as well, this can impede polymerization and acquisition of high molecular weight polymers for advanced application. And what we see here by having those termination reactions that cannot be eliminated without additional components added, those termination reactions always occur regardless of what you try. And so as propagation is occurring, you are battling against termination, and so you are eliminating the M, N, M, M higher molecular weight option as well as any MN and MM products by disproportionation. So these unwanted dead chains are being eliminated as propagation proceeds. And if you were trying to target an ultimate molecular weight, you will always be contaminated by these termination products. So that is to say your molecular weight distribution will be broad, and you'll experience what's called a high polydispersity molecular weight distribution there. So this gives us poor control in molecular weight programming. And these radicals are quite reactive, and so some chain ends have to be managed carefully. So any reactive groups positioned too closely